How do coordinate systems work for rigid bodies, especially those in rotational motion? We need to find a reference point and an axis of rotation. How should we choose them? Details on these are covered in other videos, but this video will cover a sort of general overview of this subject. The first key thing is that in order to define rotational motion, we need an axis of rotation to define it about. The axis of rotation is determined by the direction of angular velocity. So if you need to know the axis of rotation, just look for the angular velocity. What direction does it point in? So we have, for an example, a cylinder rotating about an axis of rotation, this red line here, or a general rigid body rotating about an axis of rotation that is coming out of the page and going into it. The angular velocity is pointing in these directions. Since counterclockwise rotation, angular velocity is out of the page, then it's pointing along the axis of rotation here, even though I draw it with an arrow like this to indicate that the object is rotating about this axis of rotation. It turns out that the axis of rotation is fairly arbitrary, and you can choose any axis to describe the rotational motion. So for an example, suppose we are rotating about this axis. Maybe I want to describe the rotational motion about this axis instead. One key thing to note when thinking about different axes of rotation is that for rigid bodies, the angular velocity is the same for every point on the body. So the direction of the axis will be parallel to the angular velocity, but the location of the axis on the rigid body can be arbitrary. However, although the rotational motion can be described about any axis, it introduces many complications. What you want to do is choose the rotation axis about which the object is actually physically rotating, and that will make the math simple. So we're actually physically rotating about this axis, goodbye to that axis. We'll describe the rotational motion as being motion about this axis. Very often, this means you want to choose an axis about which the object is purely rotating. The particles of the object are just moving in circles about the axis without any translational motion. For rigid bodies, the natural choice then will often be an axis through the center of mass or through a pivot point about which the rigid body is constrained to rotate. Suppose I have a spinning disk. Here's an axis of rotation through the center of mass as it rotates about the center of mass. Or suppose I have a meter stick with a hole drilled through it, and this meter stick is rocking back and forth. It is rotating about that point. It is constrained to rotate about that point. So this would be the natural point to place an axis of rotation, namely the pivot point. Because that's the point, that's the axis about which the object is actually rotating, though it is constrained to rotate in that case. One special thing about the center of mass is that for rigid bodies, the only motion about the center of mass can be rotation. So if you have an axis through the center of mass, the rigid body will be undergoing pure rotation about an axis through the center of mass, so long as you are in the appropriate reference frame, of course, that's traveling with the center of mass, even if that axis is moving or changing direction relative to another reference frame. So choose the point about which the object is actually rotating, which will either be the center of mass or a pivot point about which the rigid body is constrained to rotate. It is also true, though, that for rigid bodies moving in 2D, so just in two-dimensional motion moving in a plane, that have some rotational component of motion, and maybe some translational component too, an axis can always be found about which the rigid body is purely rotating, at least instantaneously purely rotating. This is known as the instantaneous axis of rotation, and it goes through a point that has zero velocity, so the axis is at least instantaneously a fixed rotation axis. And you will find examples of this in rolling without slipping, where the point of contact of the object with the surface that it rolls over is instantaneously at rest. So consider this object, this wheel rolling without slipping. That red axis of rotation that I drew there, that point of contact with the ground, is instantaneously at rest. It is the instantaneous axis of rotation. This rolling without slipping is only in 2 dimensions because I can contain the entire motion in just the plane. You can find more detail about that by looking into rolling without slipping. But I mention it here just to mention it is also possible to find an instantaneous axis of rotation, and that can also sometimes be a good choice to simplify the description of rotational motion. So we want to choose a rotation axis about which the object is actually rotating, and our 3 good choices are center of mass, a fixed pivot about which the object is constrained to rotate, or the instantaneous axis of rotation. So all that has to do with describing rotational motion. What if we want to calculate rotational quantities like angular momentum and torque? Well, they are not calculated about an axis. They are calculated with respect to a reference point. And all of these quantities, at least when moment of inertia is treated as a tensor quantity, see the video on moment of inertia for more on that, they all must be computed about the same reference point. If, however, we treat moment of inertia as a scalar, as we do in this course, then the moment of inertia must be calculated about an axis through the reference point. So where do we want to place this reference point? Well, you always want to place the reference point on the rotation axis. That simplifies things. And often it also simplifies things to place the origin on the reference point. So your origin is just your reference point, and it is on the rotation axis. This is done for convenience, of course. The reference point could be calculated. The reference point could be placed anywhere, and you could calculate the angular momentum and torque and moment of inertia about that point or an axis through that point anywhere. But placing the reference point on the axis of rotation and then just calculating moment of inertia about the axis of rotation through that point will make the math a lot easier and will also make the interpretation easier to understand. So a torque about the rotation axis, that's just making the object rotate faster or slower about that axis. Sometimes, though, it is simpler to take an intermediate mathematical step and compute moment of inertia about an axis that is not the rotation axis. So for an example, in the parallel axis theorem, you calculate the moment of inertia about an axis through the center of mass, and then transform that moment of inertia to be a moment of inertia about the rotation axis. And that tends to simplify calculations rather than directly computing the moment of inertia about the rotation axis that is not through the center of mass. Finally, although there can be complications with moment of inertia or torque, there is always a simple expression that the angular momentum decomposes into for calculating the angular momentum about a reference point anywhere. This will be discussed in another video, but it should be noted that even in this case, calculating this quantity, this decomposition, will become complicated unless the reference point is a natural choice that is aligned with the natural rotational motion of the system. So there you have it. The choice of rotation axis and reference point can be arbitrary, but there are some good, simple choices you can make to make the math easier.